Okay, students. After knowing something about the different aspects of stereoisomerism and optical isomerism, let us move on to the optical isomerism in tartaric acid. So, tartaric acid is the molecule which is having 4 carbon, out of which 2 are the chiral carbon. So, let me represent the chiral carbon atom by molecule star. So, these are the chiral carbon atoms. Remember. So, as the molecule is having 2 chiral carbon atoms, the n value is 2. Just 2 to the power of 2, that is equal to 4. The 4 isomers are possible for your tartaric acids. The 4 isomers are represented as structure 1, structure 2, structure 3A and structure 3B. Now, let me consider the structure 1. The structure 1 is actually active because of the absence of plane of symmetry. Let me take it as something like dextro. So, since your structure 2 is a mirror image of structure 1, when structure 1 becomes dextro, then structure 2 is inevitably evo. So, structure 1 and structure 2, both of these two are optically active because of the absence of plane of symmetry. As a result, structure 1 and 2 can be represented as enantiomers, which are nothing but non-superimposable mirror images. Okay. So, out of 4 different isomers of tartaric acid, so structure 1 and structure 2, they become, both of these two are optically active, but they rotate the plane polarizer light in opposite direction. They have identical physical properties, they have identical melting point, they have identical boiling point, they have identical refractive index, and they differ in the direction of rotating the plane polarizer light, and they also differ in their reaction with another optically active compound, and they differ in their biological activity, and of course both of them can be called as enantiomers. Whereas coming to structure 3A and 3B, please, structure 3A and 3B, even with 2 chiral carbon atoms, remember, they become optically inactive because of the presence of plane of symmetry. So you can easily observe that you can divide the molecule with this particular plane, which will give you 2 identical halves, which are related with each other as an object and mirror image. As structure 3A and 3B are having plane of symmetry, both of these two becomes optically inactive. Compounds which becomes optically inactive even with chiral carbon atom because of the presence of plane of symmetry are called meso compounds. That's what. So structure 3A and structure 3B are called as meso-tartaric acid. So, meso-tartaric acid is the one which is optically inactive because of the presence of plane of symmetry even with 2 chiral carbon atoms. Then coming to diastereomers. Diastereomers means these diastereomers are the stereoisomers which are not related with each other as an object and mirror image. Please notice this point very carefully. So, to call any 2 molecules as diastereomers, there must be stereoisomers which are not related with each other as an object and mirror image, and they are non-superimposable. Remember, structure 1 and structure 3, they are isomers, of course. But structure 1 and structure 3, they are isomers, but they are not related with each other as an object and mirror image, and they are non-superimposable on one another. Therefore, structure 1 and structure 3, they are diastereomers. Structure 1 and structure 3B, they are diastereomers. Structure 2 and structure 3A, they are diastereomers. Structures 2 and structure 3B, they are diastereomers. So that to call any 2 molecules as diastereomers, they must be stereoisomers. They must not be related with each other as an object and mirror image, and they must be non-superimposable on one another. So that diastereomers are stereoisomers not related with each other as an object and mirror image and non-superimposable on one another in a very simple manner. So you can take an example. Dextro-tartaric acid and meso-tartaric acid are the examples of diastereomers. Coming to the properties of diastereomers. They have different melting point, they have different boiling point. Because of the difference in the physical properties, They can be separated by any physical method such as fractional crystallization or fractional distillation or something like that. So coming to meso compounds which are optically inactive even with chiral carbon atom due to the presence of plane of symmetry are called meso compounds. Meso compounds, even though they have two chiral carbon atom, they become optically inactive. It is because the rotation caused by half of the molecule is compensated by rotation caused by the another half of the molecule, which is termed as internal compensation. So that meso compounds are optically inactive due to internal compensation, and because of the presence of plane of symmetry, they become optically inactive even with chiral carbon atom. Then coming to the last, racemization. It is the phenomenal process of converting an optically active compound into a racemic mixture which is optically inactive. Conversion of dextro into a racemic mixture or conversion of levo into a racemic mixture. In this process, we are going to convert an optically active compound into an optically inactive racemic mixture which contains both equimolar quantities of plus and minus isomers, which becomes optically inactive. So, conversion of an optically active compound into an optically inactive racemic mixture is called racemization. Okay.